Hello everyone, this is Rachna and from CSE 4th Sem B section, USN 162, and today I'm going to explain balanced search trees. Before learning about balanced search trees, we should have a basic knowledge about binary search tree. So what is a binary search tree? A binary search tree is a binary tree. A binary tree is where each node has at most 2 children. So if we see in this example and we take a node x, then every node which comes in the left subtree of x should have a value which is smaller than x if x is the value of this node, and every node in the right subtree should have a value which is greater than x or equal to x. Then this tree is said to be a binary search tree. So here we've taken an example where we've taken a list of elements and we should construct a binary search tree for these elements. Let's see how to do that. First we take 30. 30 will be the root node, and next element is 40. 40 is greater than 30, so it will go to the right subtree. Next, we're done with 30, we're done with 40. Next is 10. 10 is smaller than 30, so it will go to the left subtree. Next is 50. 50 is greater than 30 and greater than 40, so it will go to the right subtree. 20 is lesser than 30, but it is greater than 20, so it will go to the left and right subtree. Next is 5. 5 is lesser than 30, it is lesser than 10, so it will go to the left subtree of 10. Next 35 is greater than 30, but it is smaller than 40, so it will go to it becomes the left child of 40. So here if you see, the number of nodes in this particular tree is 1, 2, 3, 4, 5, 6, 7. 7 is the number of nodes in this particular tree, and the height of the tree is 3. To perform any insertion or deletion or searching on this particular tree, we need big O of log n time. This is the time complexity that we need to insert or delete or search in this particular tree, where this is level 1, this is level 2, and this is level 3. So the height of this tree is 3, and this is a balanced binary search tree. Now let's see how we can construct a binary search tree for this sequence of keys. First 10 will be the root node, 20 is greater than 10, 30 is greater than 20, that will go to the right subtree, 40 is again bigger than 30, next 50 is larger than 40. So here if we see, we are only building on the right subtree, so this is called as a right skewed binary search tree. The number of nodes in these is 1, 2, 3, 4, 5, so we have 5 nodes. The height of this is, so this would be level 1, this would be level 2, level 3, level 4, level 5. Height of this tree is also 5. So the time complexity for inserting, deleting and searching in this particular tree will be big O of n. So as you can see, if it is a right skewed binary search tree or a left skewed binary search tree, then it takes a complexity of big O of n. And if it was a balanced binary search tree, then it would take big O of log n, as we've seen in the previous example. So a tree can either be balanced or it can be imbalanced. If it is balanced, then the operations take big O of log n to the base 2 time complexity, and if it is imbalanced, it will take big O of n time. Next, to construct a binary search tree of the keys 10, 20 and 30 in different orders of the keys. So first we'll take 10, 20 and 30. 10 will be the root node, 20 is greater than 10 and 30 is also greater than 10. Next is 30, 20 and 10. So 30 will be the root node, 20 is smaller than 30 and 10 is smaller than 20. Next here 30 will be the root node, 10 is smaller than 30 and 20 is smaller than 30, but it is bigger than 20, bigger than 10. Next 10 is the root node, 30 is bigger than 10 and 20 is lesser than 30. 20 is the root node, 10 is smaller, 30 is bigger. 20 is the root node, 30 is bigger, 10 is smaller. So if you see, for the same, if you have taken the same set of keys, that is 10, 20 and 30, on changing the order of insertion, we are getting different. On changing the order of insertion of the keys, the shape of the binary search tree is changing. We have a right skewed binary search tree, left skewed, and here we have balanced. It changes when the insertion of the keys changes, the order of insertion of the keys changes. So if we have n keys, then the total number of binary search tree for n keys is n factorial. So here we've taken 3 keys, so the number of binary search trees that we can construct using these 3 keys is 3 factorial, which is 6 binary search trees. So as we've seen, if we have a balanced binary search tree, then the time complexity for insertion, deletion and searching is big O of log n to the base 2. And if it is imbalanced, either it is left skewed binary search tree or a right skewed binary search tree, then the time taken is big O of n. If we know the time complexities, then we'll know that log n to the base 2 is much smaller than n. And for any algorithm, we will want the time complexity to be less. So we will want to balance a particular tree and achieve a lower time complexity. So our main concern is to balance a particular tree, because we know that a minimum height binary search tree has a lower searching time. Now, how to balance a binary search tree? There are 2 methods to balance a binary search tree. First is instance simplification, and the second one is representation change. What is instance simplification? So we have a tree, and when we are constructing a tree, or when we are inserting or deleting, or we are doing some operation on that tree, if that tree becomes unbalanced at any point of time, at that particular moment of time, we will transform that tree and we will make it balanced. This is instance simplification. At that particular instance, if it is unbalanced, we will change it to balanced. An example of this is AVL trees and red-black trees. As we've seen in the construction of AVL trees, whenever there is an imbalance, we do rotation. Let it be right rotation or left rotation, left-right rotation or right-left rotation. Here, it depends on that particular instance, and whenever it gets unbalanced, we directly change it to balanced. Next, the second method is representation change. We've seen that usually a binary search tree has different nodes, and in each node there's only one item. But to balance a particular binary search tree, we're using a technique in which one node can have more than one value, and by this we can balance a particular binary search tree. An example for representation change is 2, 3 trees and B trees. That's it. Thank you.